Okay, good morning everyone. My name is Thomas. I'm a PhD student here at the University of Leicester. I'm going to talk to you today about a one-size-fits-all taphonomic model, and is that kind of approach appropriate with what we know about today in taphonomy? And this is specifically on the Mazon Creek, which is the largest that I'm working on. So the Mazon Creek, for those of you who don't know, is a 300 million year old fossil bed. It's found in Illinois in the USA. It's really famous because of its massive diversity of carboniferous organisms, but specifically also because it contains multiple, or supposed multiple environments. So you have a freshwater environment to the north and a marine environment to the south. And what's really special about these fossils is that they are preserved in concretions of iron carbonate, or siderite, and these are found in the bottom 3 meters of the Francis Creek shale member. So with any fossil bed, especially Lagerstätten deposits, what you often find is that people will have a look at these fossil beds and then try to come up with a taphonomic model which explains how preservation is occurring and why you get exceptional preservation in these sites. So these are some examples that I just randomly picked from the literature of my supervisor, Sarah Gabbett, and also some stuff that was done in Herefordshire by Paddy Orr, where they've basically come up with a singular taphonomic model to explain what's occurring in these fossil beds. And this is being done in the Mazon Creek. There's work done in the 1980s by Gordon Baird et al. But there are lots of problems with this sort of style of creating a one-size-fits-all model. They don't consider things like decay prior to lithification. They assume that all organic matter has the same preservational pathways, and they don't explain why some of these concretions don't have any fossils in it at all. So it's my job to try and work out what's happening. But the thing that I'm really interested in is decay prior to lithification. So, is a one-size-fits-all taphonomic model appropriate for the Mazon Creek? There are 2 approaches that we can do to look at this. And the most basic and fundamental, and if you think about it, the most obvious, is to investigate modes of preservation. So in order to do this, we look at a tree of as many different organisms as we can that are within the creek. And from there, we can then go on and investigate modes of preservation across the tree. So if I choose one, for example, which are the chitons, we have some beautifully preserved chitons in the Mazon Creek. And then we can do some really basic things like identify key morphological characters, work out if they're consistently preserved, are there any tissues missing, are there biases that are occurring on organic tissues, and are the modes of preservation shared across taxa. So just for example, I chose some random characters such as a head, a radula, and girdles, etc. And then we can map on what they're preserved as. So in the Mazon Creek, things are often preserved as kaolinite, moldic, stains, metalliferous, and some are preserved as organic. And we can map that on. And then if we wanted to, we could choose something like, I don't know, like chitin, and then we could map that across the tree. And we could see if there are any biases which are occurring on specific tissue types. And that's really important to allow us to determine how decay and modes of preservation are affecting these fossils in this fossil bed. And if you think about all the work that you're going to see today on fossil completeness, on trying to work out whether sauropodomorphs change through time, all of this is dependent on taphonomy, so it's really important for us to get this right. But then the second approach, and this is what I really want to focus on today, okay, is investigating what we call the decay spectra, and that's work that we're really pioneering here at Leicester. So if you think about it, can we elucidate decay pathways from fossils? Can we actually work out what has happened to a fossil from the moment it died all the way through until it becoming a fossil? And that's kind of obvious, right? Think about dinosaurs, dinosaur bones, all the flesh is pretty much gone, so you're left with just the bones. But what about soft tissue taxa, things like polychaetes? Polychaetes are a really great thing to study. We can get them by the bucket loads, quite literally. They're quite cheap. Also, there's loads of experimental data on them. But the reason why I really like them is because we've done lots of work on them here. So people like Duncan Murdoch, who sat at the back, who gave the workshop yesterday, he's rotted these things and basically looked at what happens to these organisms as they decay through time. Okay? And you need to think about decay slightly differently. Decay is basically just the loss of characters through time, the loss of morphological characters through time, which is kind of obvious, really. But the other reason why I really love polychaetes is because the Mazon Creek is absolutely chock-a-block full of these exceptionally preserved polychaetes. And although you can't really see them very much because the light's a bit bright, what you can see here is that the soft tissues remain, and you've got lots and lots of characters. And within one geographical site, we have huge numbers of samples that we can study, and we can also study polychaetes from different families and start to compare them against each other. So I went to institutions all over the world. Most of the big Mazon Creek collections are over in North America, and I catalogued hundreds of specimens, thousands actually, of specimens of polychaetes. And we removed from our analyses any which were ambiguous or not complete. They have to be complete. And so I think we got 370 odd specimens. We rejected 630. We actually rejected thousands more, but they were very ambiguous. They're just like sort of blobs on the concretions, and you can't really see them. And we ended up with about 120 of one family, 80 of another, and 170 of another. Okay, so what's the next step? So from there, we need to identify morphological characters that these polychaetes have. And we do that by looking at the holotype and then trying to identify as many characters as we can. And we also use extant data, and we look at modern relatives that are still alive today, and we basically create a morphological character list. And then what we do is we can ground truth those morphological characters once we've identified them on the fossil itself by using things like SEM, EDX, and that will allow us to actually work out what these morphological characters are now preserved as. So when I talked to you earlier about the caolinite and metalliferous and things like that. And then you create something that looks a bit like this. It's a bit horrific, but basically this is just a presence or absence data table. Okay, so if the character is the samples at the top, if the character is given a 1, that means it's present. If it's absent, then it's a 0. And then we code on the colour, which is its mode of preservation. And we'll talk about that in a little bit. And then what we can do is we can look at how many times that character is present across all the samples of the polychaetes. And we can give the character what we now call a retention index. And this is work that's been pioneered by Sarah and Mark and also by Duncan. And basically what you do is you give it this retention index. And that's really useful because then we can then start to compare the retention indices across the polychaetes. And so what we find that's really interesting, this sounds really simple by the way, like it's in 3 slides, but it takes absolutely ages compiling the data. And then you get spat out with 3 little numbers. Which basically what it shows is that statistically, that they correlate, which is really interesting because what it tells us is that in studies on decaying polychaetes, what's been found is that character loss is not random. Okay? It occurs in a set sequence every time. And what these little numbers that show statistical significance at the bottom show that these polychaetes, not only are they consistently losing the same characters at the same time, okay, but that's the same across different families of polychaetes. So what we can actually say for the first time ever in the Mazon Creek is that these polychaetes are undergoing exactly the same decay trajectories as each other. And that's really important if you think about it at a fundamental level, because what's often thought of in paleontology is that 2 fossils are completely non-comparable because they have their own unique taphonomy, their own little story from death all the way through preservation. And we can quantifiably say for the first time that actually in these polychaetes they're all going through the same processes of decay. Okay, there's no differences in them. The next step then is to compare it to the rotten polychaetes that we have in the lab downstairs and to see if it matches. And what we're actually finding, and this is work that I'm still doing at the moment, so I'm not actually going to present the raw data, but what we're finding is actually there is no statistical correlation between the polychaetes from the Mazon Creek and the polychaetes in the lab. And we're not really sure why that is yet, but some of the hypotheses that we're going to be testing further is it could be that they're just not decaying in the same way than if you just decay it in water, or it could be conversely that there is something influencing the preservation and the modes of preservation that are influencing the polychaetes in the Mazon Creek. So there's some difference that we need to disentangle now. And then that basically leads on to mapping the characters. Are the modes of preservation biasing what characters we're seeing in the fossil record? And that's super important, because if your hard parts are only being preserved by one mode of preservation, but that mode of preservation has a bias against it, then you're going to massively skew your data when looking at completeness in the fossil record. And as you can see in these 3 different polychaete groups, there's a huge variation in modes of preservation, even within characters that are the same. So for instance, in body outline, obviously the body outline isn't the same in all of them, there has a huge variation in their modes of preservation. So this is a really complex story, but we're starting to sort of ravel and disentangle this sort of horrendous taphonomical mess and sort of actually elucidate what's happening to these soft tissues as these things are rotting. So then just quickly to sum up, basically there are lots of broad scale patterns in the Mazon Creek as across disparate groups, which is really great if you're creating a one-size-fits-all taphonomic model. But within a single taxon found within a specific locality, morphological characters are preserved in this sort of variety of preservational modes. Similar patterns seem to occur within the same families, but the retention indices demonstrate that fossils from the same locality undergo the same decay processes. There's not this huge variation that's been previously hypothesized. However, possibly not the same as controlled decay experiments. And lastly, mapping modes of preservation may elucidate why there's this difference between the extant polychaetes being rotted and the Mazon Creek stuff. So thank you very much. I'd like to thank my sponsors at NERC and at the Palace, and also my supervisors, Sarah and Mark, and ask if you have any questions.